My name is Marianne Bellotti, and today I'm going to talk to you about future-proofing systems. Like, what can you learn from some of the oldest software systems in the world? So, quick introduction. I currently run core services at a company called Rebellion Defense, my area focuses specifically on identity. So that means that today I work in all modern systems, but for a very long time, the focus of my career were very old computer systems, like 30 years and older. Let's just get something right out of the way. In my mind, there's a difference between legacy systems and tech debt. And so this is something I like to put in people's minds right from the get-go, because we tend to talk about these terms interchangeably. And in truth, on old systems, you will see evidence of both, but they're actually kind of different concepts. A legacy system is a system that has a certain degree of consistency to itself based on the way it was originally designed, but it's simply not been updated or upgraded or really for a long period of time. So the types of problems you see that are legacy problems are things like stuff is undocumented, or the documentation has been lost, or the documentation is out of date. You're many upgrades behind, so it still could be the world's most beautiful algorithms that were written, but it's written on a version of Node that is end of life, or was end of life like 3 years ago, sort of thing. And then frequently, a lot of these systems don't really have any kind of testing on them, so you have a hard time. You don't know how they're supposed to work because there's no documentation, and you also can't figure out how they're supposed to work because there are no tests. Technical debt, on the other hand, is a product of change, is a product of churn. So you're generally, when you're looking at systems with high degrees of technical debt, you're looking at systems that are internally inconsistent. That might mean that there are partial migrations. There was a point where we tried to change something and then it got too hard or didn't work out the way we wanted it to. And we either stopped that migration or we attempted to go back. That may be that we, rather than doing rewrites and like restructuring our technology, we did a bunch of workarounds and some cheap hacks, and there's all sorts of like strange things hidden in the code. And so these are two distinct concepts, and often in old systems we'll see a little bit of both, but I think it's important to just kind of have in your mind a picture of like what it means to be legacy versus what it means to just be overwhelmed with technical debt. And the other thing I like to stress about old systems is that old systems are successful systems. It's very easy for people to be extremely cynical about old systems, especially like the old COBOL mainframes, but these systems are still around because people use them, and often they're critical, which makes them even harder to shut down. If that wasn't true, then we would just pull the plug, turn them off, and that migration would be super easy because no one is using it. So the important thing to remember about old systems when you do encounter them is that they were successful in what they set out to do, and often they were exceptional in what they set out to do. So what kind of problems do old systems have? The first one I mentioned already, loss of institutional memory. There's no documentation. The documentation is out of date. Often the people who built it originally are no longer work there. And worst case scenarios, the people who built it originally may in fact be dead, so you're out of luck altogether. There's also an issue of lack of experienced staff. This is particularly a problem when you're dealing with things like COBOL. Like COBOL itself is not a difficult language to learn, but if you think about the amount of experience and expertise you need to kind of navigate through a large, complex application when it's written in anything, and like know just instinctually, this is structured this way, but it would be better if it's structured that way. If you think about the level of knowledge and experience you need to do that in any language, then you start to understand what the problem is with when people talk about the shortage of COBOL programmers. It's not that we can't get more COBOL programmers. It's just that we have trouble developing COBOL programmers in a way that they will have that expertise that they can tackle these like really big old systems. And then the third problem that we frequently have with old systems is that there are blockers to integrating them with modern systems. We change protocols, we change approaches. There are different trends throughout technology, and sometimes the expectations and assumptions of the old system are no longer relevant on modern systems, and we have to figure out how to like piece them together. I have had the unfortunate experience of having web apps talk to COBOL mainframes many times before, and it's never fun, and it never really makes a great deal of sense. So most engineers kind of have this attitude of like, well, that's fine. I'll just not work on old systems because like I'll just work on new systems and then I'll never have to worry or think about this at all. And the reason why I think that is kind of short-sighted is that ultimately every old system was a new system once. So you learn a lot by looking at how technology ages, and it changes the way that you build your new systems. And in particular, I think people tend to have this idea that there exists the perfect technology. And so you'll see this all the time on like Reddit and Hacker News, where something new comes out and now all of a sudden everybody wants to put that everything they have in that new thing. So like everything had to be on Ruby on Rails at one point in my career. And then everything had to be in MongoDB at one point in my career. And like now I don't even know, maybe it's like something like Darklang or something like that. There's, to guarantee you, there's a language or a technology that everyone is saying, this is the solution to every possible use case of like this need. And it's never true because there is no idea of perfect technology. And when you work with old systems, you start to get a finer tune awareness for that than when you work just exclusively with new systems, because you sort of see how this old kind of untrendy, uncool technology, what its strengths are and what its weaknesses are. And that makes you look differently at the things that are being pushed at you as like these great advancements in technology. In general, what I try to tell people is that technology actually advances in cycles. We reuse patterns and principles over and over and over again. Like we will have like, it sort of ebbs and flows. And so the example I love to give people is like, what is the difference between cloud computing and time sharing on mainframes? When you think about it, it's a big, expensive piece of hardware that you don't want to buy and maintain. And so somebody else buys and maintains it and rents it out. It's sort of the same model. So we went from having this one model to moving to like everybody has PCs and we all work from our like desktop applications to going back to this model of like how we process data. So all through technology, when you start to dig into its history, you'll start to see these cycles going around and around and around. And like working with old systems gives you a real appreciation for that. How do new systems go bad, right? So these are the three things that I always highlight for teams that want to build a new system, whether they're building a new system to replace an old system or whether they're building like a completely new system. The first and most critical part is your maintenance strategy. And I'm going to go into depth on this in a minute. And then the second thing that's really important is the impulse to put cool hacks and workarounds in production. And then the last thing we're going to cover on this topic is prioritizing new over value add. So let's dig into maintenance strategy. What does it mean to have a no or unrealistic maintenance strategy? So when I spent like 3.5 years working for an organization called United States Digital Service, and that was really where I did the bulk of the worst of my legacy modernization work. They were putting me on systems that were built in like 1968 and were still running, and nobody could figure out how to get rid of them. And a problem that we would have at USDS a lot is that we would have people come in to run projects for us who would have this kind of attitude. They would come to the government and they would look at the old system and the failing project to replace it, and they go, okay, this is how we're going to solve this problem. We're going to go over here with our team of people and we're going to build you the most amazing website you've ever seen. And then we're going to bring it back and we're going to dump it on you. And you're not going to know the technology because we didn't build it in something that your people know how to program in. And you're not going to know what it does. And you're not going to know how to maintain it. And then we're going to leave. And what would inevitably happen is that all forms of technology need to evolve. And so at some point, this beautiful, perfect website that was just built in the most exacting standards would need to be updated, right? Something would need to be added, something would need to be changed. And then the people who were in charge of maintaining it would have absolutely no idea how to do it. So they either wouldn't do it at all, and it would be out of date and therefore like progressively less useful over time, or they would break it in a way that either created lots of security problems or lots of scalability problems and ultimately made it a weaker thing. So there's a real like pull that people have to taking work away from the people who ultimately should be maintaining it. I see this everywhere I go. It's like, oh, it's just easier if I do it for you. And it's like, really, really not. So the thing to remember, kind of the cardinal rule here, is the people who are going to earn things long-term have to be there when it's being built. They don't have to be the tech lead. They don't have to be the main driving force, but they have to be involved. You have to carry them along with you, and you have to make sure that they understand what you're doing and what you're using. And if you're going to use a new piece of technology, you have to make sure that they are trained to use it, or that they can hire people who have been trained to use it. So there's no perfect technology that never needs to be updated, and a system built in a way that ultimately the owners can't understand that will just result in them breaking it. And then the last thing that I like to emphasize to people on this point is that we tend to think of our career growth as we go from like junior engineers into senior, into staff, principal, so on and so forth, whatever silly job titles come after principal, that the line in that progression is about more knowledge and just getting more expertise and learning more things. And there, you will learn more things as you advance your career, but the line between the most senior engineers and sort of the middle ones isn't that they know more about technology. It's that they are mentors and that they've built up their skill transferring knowledge to others. And so that's an important thing to understand here, is that even if you build a team where the people building the product are the long-term owners, eventually those people are going to want to leave. So they need to have the skill sets to transfer this knowledge to their more junior teammates and bring them up, who transfer it to their more junior teammates and bring them up, so that you are always constantly refreshing and like re-engaging that expertise. Okay, so we move on to the second thing, workarounds. I tell these people this all the time. Once it's in production, it's never coming out of production, right? Never coming out of production. So think very carefully when you're thinking to yourself, oh, I don't know the right way to do this, but I think this will work for right now, is that once that goes into production, the odds that it will ever come out of production are just tiny, absolutely tiny. Decommissioning services is the hardest part of my job. It is the thing that takes the longest to do. And the longer something is in production, the more things have been built up around it, which means the more things are dependent upon it. So even like tiny, tiny pieces of code that seem so harmless and seem so easy to get rid of become so difficult to get rid of, because when you change them, you break the contract with like 20 different services, right? Workarounds also tend to produce more workarounds as you go along, because if you weren't willing to invest the time and energy to like refactor and architect and rethink the system in the first place, you're unlikely to be willing to invest that energy later on. So you end up kind of drifting, the product ends up drifting further and further away from the original vision, and ends up having more and more workarounds, which make it more brittle and harder to document and just increase your technical debt. And then the last thing is that like, well, something may work for you locally, but if it's not the right way to do it, you actually have no way of knowing what its consequences are at scale. So this is a problem that I deal with quite frequently now, because we have to produce products that have to operate on a giant scale right away. Like we work with the government, and the government doesn't work in like tens of users or hundreds of users. The government works in thousands to millions of people at a time. And so we don't have much grace period where we get to like build something in a cheap kind of prototype way and then like figure out what people like and then iterate on it. Like a lot of times we have to build at scale immediately. And so if we are doing these short, quick hacks and workarounds, we get bit very, very quickly on that. Okay, last part of this section. Prioritizing new over value add. And so I touched on this a little bit earlier, that there is this compulsion to see new things as inherently better as old things. And so every time I come onto a new software project, there's always somebody saying, you know, this thing would be so much better if we put it on like Kubernetes or the blockchain, or I don't know, whatever, like insert whatever the hotness is now. It's really important to be able to articulate why it will be better, and not just because this is a new thing that's cool. So for example, some questions you can ask is like, what is the purpose of this new thing you're adding? Like, why is it going to be better? What value does it bring versus what we have? And to remember that new is not necessarily better. So thing I emphasize for people is mainframes are really, really, really fast. They are really, really fast. They're about the size of refrigerators now, but they're really fast. And like things like COBOL and Fortran are really good at math. So like these old forms of technology that we're so cynical about have their advantages in certain situations. And the new forms of technology that maybe I'm a bit skeptical of also have their advantages in certain situations. And so understand what those advantages actually are, and like design how you want to modernize things based on actual value add, rather than just, I am ashamed of this technology because it is old and gross, and I want to be on something that is cool and will make me feel good about what my LinkedIn profile says, right? Because new technology can make existing systems more expensive, it can make them slower, it can make them less reliable, which then ultimately means that if you're trying to migrate a large system onto something else, you don't get all the way there, because every organization, every engineering organization I've ever worked for in the private sector, in the public sector, in the government, has had some business component that they ultimately had to respond to and justify what they were spending their money on and what they were spending their time on. So the example I give people for this is this idea of cloud computing. Yes, most use cases, 9 times out of 10, using the cloud for something will be cheaper. But there are small cases where it's not. It's actually dramatically more expensive. And the best example I can give people of that is large-scale data processing. If your data lives in a data center, moving it into the cloud to run it on a Hadoop cluster and then moving it out of the cloud to go back to where it needs to be is going to cost you an insane amount of money and not really bring much benefit, versus having a rack of servers where you're running your own Hadoop cluster in the data center where the data already lives and where the data has to go back to. So, just try to factor in these things and understand the value add that new technology is bringing to the table when you approach it. Okay, so that's about legacy. Let's dig into the future-proofing part of the conversation, the thing people are interested in. I like to clarify first that future-proofing is not about building it perfect the first time. That is impossible. Future-proofing is about evolving technology gracefully and strategically, so that you don't end up in a situation where you have this really old system that is profoundly broken and no one knows what to do with. Okay, so there are 2 types of issues that require us to rethink technology when we're maintaining. The first are usage changes, things that you're probably familiar with, scaling changes. And then the second are what I call deterioration. So we're going to go through exactly what these 2 things are. Start with usage changes. Usage changes can be things like more traffic, and they can be things like different types of traffic. They can be things like we added a bunch of features and the product inherently changed. So a good example of that last one is when Twitter first started, it was essentially a kind of group texting platform that was public. And now, if it's anything, it's how people really discover news. And those are 2 completely different things. And along the way, there was a whole bunch of product changes, a whole bunch of feature changes. But those feature changes also changed the behavior of the users, which changed the systems that got hit more often, which changed the scaling. So we can think about usage changes in the traditional scaling use case of like you had 10 users and now you have 1,000 users and now you have 1 million users. We can think about usage changes in the terms of you were getting mostly people coming from web browsers versus you're getting mostly mobile phones versus you're getting mostly bots, which if you sell shoes online is apparently your reality now. Or we can think about usage changes in terms of the number of users is the same and the types of traffic is the same, but the behaviors and the interactions on the site and the way that affects the downstream services are different. The thing to understand about usage changes is that they're hard to predict because there's no set cadence around them. Like in theory, you might see a predictable linear line of growth. You might see a hockey stick line of growth. You might see no growth at all. So you could see a scaling change in 5 weeks of launching a product. You could see it in 5 years, or it might never happen at all. And so because there's no predictable cadence to them, it makes it harder to put usage changes in as part of the normal routine. Deterioration. So the second thing, deteriorations are things that are inevitable. They have a linear progression. We may accelerate or decelerate along that linear progression, but we know it's coming and we have a general idea of when it's coming. And because of that, they become more dangerous than usage changes because they become part of the normal routine, and therefore it is easier to forget about them or ignore them or neglect them. So here's some examples of deterioration. All hardware will fail eventually. Any disks or racks of servers that you have will eventually fail. And like usually they fail within a certain time scale, depending on what they are. And if you use them more often, they may fail earlier. And if you use them not so often, they may fail later. But like we know they're going to fail, and we know about when they're going to fail. Language and tool updates, same thing. Like all languages are going to have updates. They're going to have patches. Your OS is going to have updates. They're going to have patches. If they stop having updates, then you have to move off them eventually because they will no longer be secure. So you don't even escape it when they stop maintaining whatever it is you're using. So we have a fairly good idea of like where the cadence of that is. It may speed up, it may slow down, but we generally know that like if we look at the history of the maintainer and how they've progressed, we can generally feel like order of magnitude exactly where it is. And then things like memory leaks, again, like you may use something more or less, and that may affect when the memory leak really becomes problematic, but you see it coming and you know it eventually will bite you in the ass. And then the last one, the one that I like to talk about in the most depth, is time overflows and rollovers. And I've put in here 2038. Does anyone know what 2038 is? Actually, I don't know if they can unmute.
Everyone should be able to unmute.
Yeah, nope, I've never heard of it.
Cool. 2038. Yep, sorry.
Sorry, I was going to say, if you have a 32-bit integer, you can't have a Unix timestamp that's greater than the year 2038. So it will overflow, so it will go back to 1970, which can cause problems. Yeah.
So 2038 is when Unix's timestamp for 30-bit computers rolls over. And we've already seen problems on this. We've already seen problems on this in the financial world, because they do calculations like 10, 20, 30 years out. So when they're hitting those calculations that are, I suppose they were in 2018, so they were hitting the 20-year out mark, they were hitting this overflow problem and having problems. So we've already seen this problem. You can think of these as like Y2K. Like that's the simplest example that people know about. You had a 2-digit year, and then suddenly, wait, we're not going to get the right thing out of it. And they're really interesting because people always kind of assume, especially when you talk about Y2K, people go, well, that was stupid. Why didn't they just use a 4-digit year? Like, that's dumb. Why did they use a 2-digit year? And the reason why they used a 2-digit year is because we don't have infinite memory. So you have to make this choice about like the more space you give to storing time, the more space you're going to have before you overflow, but also the more memory you don't have for other things. So they made this decision to store 2 digits because they had smaller, well, they actually had physically larger computers, but they had smaller in terms of like processing power and resource computers, and they didn't want to spend their time in storing time. But because we don't have infinite memory and we have to make that choice, any system storing time will eventually overflow at some point, right? And when we're approaching this, the actual problem is relatively easy to solve. It's not the hardest technical challenge in the world. Like leap seconds get a little bit wonky, but like otherwise the time overflow problems tend to be relatively easy to patch. The problem with them is that we tend to forget about them. We tend to forget that they're coming, and then they sneak up on us. And we also ultimately assume that what we're building now won't be around 30 years from now, 40 years from now, 50 years from now. Think about what you're building right now, and now think of it existing in this world 30 years from now. And like, how likely do you think that is to happen? And no one ever thinks that it's going to happen, but it's actually not that unusual for technology to stick around for a long period of time. So like, these are 3 very, very extreme examples of that. If you know anything about the New York City subway system, then you know that we are still using control panels from the 1930s. And this is always a big news story whenever one of them lights on fire, right? And then everybody's like, what the hell? Like, this is ridiculous. Why is the biggest subway system I think it is actually the biggest subway system in the world, of this city of 10 million people, running on such old technology? There's a cathedral clock in Salisbury that has been running since 1368. This one is my favorite. There is a light bulb called the Centurion light bulb on top of the Livermore, California Fire Station 6 that has been on since 1901. That is mind-blowing to me. I don't know what's going to happen when it burns out. I think it'll probably be a major news story, and then they'll have to figure out, does the socket fit LEDs or something? But like, technology can persist far beyond what our mental expiration date for it is. So the thing to ask yourself with deteriorations is, how do we make this fail gracefully? So first, anticipate where the deteriorations are in a system when you're building it. Like, where are there time problems? Are there hardware problems? Where are you going to get bit by this? And then to try to figure out what fail gracefully is in the context of what you're building. So this may not be what you expect it to be, right? This could be that it panics and quits, right? That could be fail gracefully. It depends what you're building is doing. So if a panic would cause, if ignoring the error and moving on would cause data corruption, then ignoring and moving on is not failing gracefully, because data corruption, especially if it cascades through multiple systems, is just a nightmare to like untangle. And so the failing gracefully in that use case may actually be that we panic, we stop, and because it's a batch job and we can just rerun it. So we throw off an error, we alert somebody, and that's it. So we got to figure out, like, given what you're doing and what the system is supposed to be doing and how the system is likely to be used, what does it mean to fail gracefully in that situation? And then the second thing that I like to push people to do is actually to fail more often. I'm not fond of these fixes for time problems in particular that push the date out another 30 years or 40 years or like 100 years now, because if you look at the data, especially GPS rollover. If you look at leap seconds and GPS rollovers, and you look at the people actually working in these spaces in places where we've had massive like cross-industry problems based on overflow issues, the more time there is in between migration issues where you had to do it once and now you have to do it again, two things happen. First, people have built more and more and more and more on top of that assumption. And second, new technology has come into play that did not factor in this issue at all. So the best example is GPS rollovers. The first one, I think, was in the late 80s, early 90s. I actually can't remember the date off the top of my head now. But it was relatively quiet and caused no problems whatsoever because nobody was using GPS. Like, GPS hadn't really taken off as a form of technology. And then the following one, the one immediately after that, was after the rise of the smartphone devices, right? So now everybody has an iPhone, everybody has like their Android smartphone, everyone is using GPS all the time, and it's hooked into everything. And it became this massive, like, oh my God, how do we fix this problem sort of moment? So the more time you put in between these kind of failures, the less people know how to deal with them, the less comfortable they are with them, the more likely they are to forget about them. And so I actually think that in most cases, it is useful to fail more often rather than build things as if it will never fail. So I tend to call, like, my philosophy about building new systems, build it wrong, but build it wrong the correct way. And so the first principle of that is to kind of think smartly about coupling and complexity. So these are concepts we talk about a lot in architecture. For those of you like a little bit less familiar, I'll just run through it. Like, coupling is this idea of you have two services or two parts that are really tightly connected so that one fails, the other one will fail. Like, they're really tightly connected. And you loosen that coupling so that if one fails, it doesn't necessarily affect the other one. And that is a goal for a lot of distributed architectures. But the other side of that is complexity, meaning like how many services, how many moving parts you have. And that's also very problematic in a lot of ways. So the thing to understand is that we often talk about these concepts as if they are separate, and I'll listen to engineers talk about how they want loosely coupled but low complexity systems. And I'm like, I don't understand how that is a thing that is possible. Because if you uncouple the system, you generally uncouple it by adding things to it to make it fault tolerant. So for example, if you have a monolith and you break it up into services, and then you can scale those services independently of one another, so it scales better. You now need to put load balancers in front of those services and figure out how they talk to one another and how they keep in sync with one another, right? So you've added another layer to something that was very simple. So there's often a trade-off between the level of complexity and the level of coupling. When you loosen the coupling, it adds complexity. When you minimize complexity, it's usually because you're reusing things, which means you're tightening the coupling. So understand the pros and cons of these things, right? Complex systems can be easier to scale, but they take more people to run. And coupled systems or monoliths can be easier to understand and sometimes easier to change, but they can be these hulk of systems that are difficult to move and difficult to like work with and scale over time. Okay, so I typically talk about these things in terms of staffing, which is admittedly not the way most software engineers talk about them. This is why I run teams. And so the thing to understand about the way we think about complexity and coupling is that a complex system is ultimately made of stable systems. So the question of how complex your system can get for you to be able to maintain it and ultimately evolve it correctly is how many people do you have, right? So what I tell people is an on-call rotation, the minimum I will do an on-call rotation is 6 people, because I like to have the first track, that's the actual on-call people, and the second track, which is the backup secondary. So if the first person fails, there's a second person that's got their back before we burn out our SLO. So if you think of an on-call rotation as being 6 people, how many groups of 6 or around 6 do you have on the team that's maintaining the thing you're building? If you have a 5-person team, then you're probably going to want to build something that's very tightly coupled and looks like a monolith, because you only really have one stable system that you can maintain. If you have a 2-person team, then you might want to split that up into 2 services, because now you're a little bit bigger. If you have a 50-person team, then now you can start to bring all these complex things like service meshes and like all the trappings of distributed computing to the mix, because you actually have the staff on hand to really maintain that and organize it really well. Okay, so I absolutely wanted to leave a little bit extra time at the end of this for questions you might have and like stories I could tell, but I'll add 2 things to the end of my presentation. First, if I have piqued your interest in this stuff, I have a book coming out in February from No Starch Press called Kill It With Fire that goes into detail about how to run legacy modernizations and like think about technology. And also you can just follow me on Twitter or Medium, which is where I generally post my writing on a normal day. So that's about it for me. I'd love to like hear your reactions and questions if you have any.
Cool. Well, thank you so much for doing this session. Has anyone got any questions they can put in the Zoom chat, or you're welcome to unmute your microphones?
Yes,
so someone
when
asks,
you're building.
Yeah, go ahead, Taimur.
So I was going to say, when you're building a system that's like, when you're trying to like justify it to the person commissioning the system, like, you know, we should future-proof this. If they're on a relatively tight budget and they're getting paid for like rolling it out as quickly as possible, which people often are, like, what strategies do you use to try and convince people that it's worth the extra overhead of designing it well and making sure that it will continue to work?
Yeah, so this goes back to the question of value add. Being able to communicate what the value add of technical decisions are to the business layer is invaluable. And admittedly, it takes a lot of practice. When I usually don't come in when the system is being built initially. I usually come in after the system has been running and they're trying to figure out how to solve problems with it. So my approach is a malicious form of crisis management, to be truthful. I used to say that my job was to get the right people to panic about the right things in exactly the right amount. Like, we would find things that we could document were wrong that would like have critical business effects, and we would demonstrate that for them and then go, this is the way we're going to solve that problem. And like, just sort of think about how we wanted the architecture to look and then break that down into where can we find problems that will justify these changes, and like have that conversation that way. If you're coming in to a new system, and I would say that most people think about how they do engineering as if they are going to start from scratch. And actually, I think you will find that it is very rare that you will have the opportunity to start from scratch. But if you are coming in from scratch, I would say really lean hard into the idea of a minimum viable product, and like really challenge that minimum viable product is minimum. Because when you're thinking about something in terms of, it's not a full-blown product that has many different features for 1,001 different potential users, but you're thinking about things in terms of like, it is the smallest possible iteration in order to prove that there is market value. A lot of those architecture decisions are just straightforward, like way easier, because the actual space that you're building is much smaller, right?
Yeah, thanks.
Cool. So we've had a question in the Zoom chat from Kaffel, which says, would it be hard to go from COBOL for like 5 years to something like JS?
I don't think so. It depends on the person. Like, there are some people that genuinely love to learn and to kind of like self-start, and like, there is not a lot of overlap between COBOL and a lot of modern languages, which to me is super interesting. I've done a lot of writing about why that is, like why the heritage of computer programming languages basically came up through C rather than these languages that were just way more popular and way more prevalently used. But it is what it is. So there's not a lot of overlap in terms of, oh, I've seen this pattern before between COBOL and something like JS. But that being said, the process of learning both of those languages is the process of learning any software language. And so if you've already learned one language, you can probably learn another language just as easily. It's really about, like, I would say it's more about the kind of dirty aspect of your career, right? Do you want to start from scratch? Because if you're a person that spent a lot of time developing expertise in one language, and you're literally have no basis, no foundation whatsoever in something like JS, which is not only a different language, it's an entirely different paradigm of language, you're not going to start from the senior engineering level there. You're going to start from a lower level. And like, how comfortable do you feel starting over and starting from scratch and like basically being the newbie and then working your way up? I think that is generally a larger blocker than anything specific to the language.
Cool. Has anyone else got any questions? You're more than welcome to unmute your microphones, or you can type it in the Zoom chat.
Hello.
Hello.
Yeah, Marianne, thank you for your talk. It was very informative. So I'm dealing with a legacy system which is written in Perl, and so that's around, it's 15 years old, and the client has agreed to that I can start some modules in Python or in Elixir. Mm-hmm. So what are your thoughts on that? And also I would love to hear your thoughts if you have utilized any brownfield methodologies to add new functionality to an existing legacy system.
Can you clarify what you mean by brownfield methodologies?
Yeah, brownfield has its origins, but it's now used in software development as a way to deal with legacy code. Am I cut off?
Nope.
Oh, sorry. Yeah. So what they say is a brownfield is so you have a legacy system, and if you think of a system as a let's say 10 buildings, and you need to demolish a building, what do? You put fireworks at the root of the building, and you take it one building down at a time. So that's the way you demolish the building without affecting the surrounding modules, right? I'm just giving an analogy of structures of towers. So brownfield says that, okay, I don't want to I want to demolish one tower at a time. Let me demolish that tower without affecting the other towers around, and then I'll focus on building the new tower. So yeah, that's an analogy for brownfield.
Okay. Yeah. So I'm not a huge fan of that because I think ultimately systems end up becoming very enmeshed together. So the odds that you're going to be able to take one part of it down and nothing else is going to mind that it's offline and then build another one are very low. The other technique that sounds very similar to what you're describing is like basically hard switchover, right? You've built the new system, you're just going to turn the old system off and then put the new system up all at once. And that I try to discourage people from doing that because it is very, especially if there's data running through this system, it's very difficult to know every single edge case of a live production system. So you may think we have got this perfect. It is absolutely a complete facsimile of its data contracts to what was there. It's just built better under the hood. You may think that you get that, and then you get it in production, and if something goes wrong, and you can't go back, right? So that can be very stressful and very problematic for people to do. I, in general, prefer kind of something similar to a blue-green way of doing it, where we put the new system up and we feed it a little bit of traffic and see how it goes. And how it runs compared to the old system, and then we feed it a little bit more bit of traffic and a little bit more bit of traffic, and we sort of gracefully phase out the old system. That is my preference. That's not always possible, but that's just my preference on things. The one place where I do kind of do hard cutoffs is where there are relatively clean lines with a system, and I'm actually blanking on an example of that. But if a component is small and we know for a fact that there are very few dependencies on it, I might go, yeah, let's just turn it off and replace it wholesale. Like, okay, now just remember my example of this, like front end stuff, right? Like front end stuff, I think it's generally okay to just like turn one system off and turn another thing on. But even when you look at like when Facebook does a redesign, they don't do that, right? They do more of the blue-green. So it's ultimately up to people, but I tend to prefer to like more gracefully fade it out. As for Perl and Python, like that sounds great. I mean, like they keep telling me Perl is going to come back, but I am very skeptical that will ever be a thing. So that sounds like a great thing. I don't know if you wanted to be more specific than that.
Yeah, I mean, I started my career with Perl, so I still love Perl programming, but I'm doing a lot of Python and Elixir these days. So I definitely want to use Python microservices. I can do it in Perl too. But since I'm working professionally, the client also has a request that, you know, I need new developers to join, and I'm not getting any developers in Perl. I'm getting a lot of developers in Python. So it's also a case where the problem of available skill set. So yeah, that's just a question I had. It's just a little troubling for me also.
Perfect. Well, thank you for those questions. Has anyone else got any final questions before we wrap things up? Gonna give everyone a few seconds. Sometimes I'll be like, okay, that's everything. And then there's someone frantically trying to type in the chat.
There's like, what's an incentive to work on very old systems and pay? I don't know if this is a question or if we answered this one already.
I don't know if it's a question, but feel free to cover it.
We answered this one already. Okay, sorry.
Cool. Loving some of the comments that people were saying during it, such as, hey, anyone want to retire from retirement to fix our banks?
It's true.
Yeah, what does this part of the code do? $500 and you get the secret sauce. Yeah, true. Well, I think that's everything. If anyone does have any other questions, you can let me know and I can email out some of those questions. But thank you everyone for attending.
Just tweet.
Or you can tweet Twitter handle on the screen at Belmar. There we go. But if anyone does have any more questions, you know what to do. But I think that's everything. So thank you so much everyone for attending.